Hello everyone, welcome to my channel. In this series, I would like to show you those most commonly assessed questions in A-level math. Okay, and in this particular video, I would like to talk about distributions again. Okay, so following from the previous video, I would like to show you furthermore about discrete random variables. The concept might be similar to the previous one. Okay, and if you haven't watched it, please have a look because it's a nice nice warm-up for this question. This one gets interestingly difficult. Let's just recap what I'll talk about here. Discrete random variables. Those are random variables that assign probabilities to countable amounts of events. And the most important part is the sum of all the events is 1. Right, and we'll probably need to use it again here. Right, let's now begin. In this question, we show detailed reasoning. The random variable x has probability distribution defined as follows. P capital X is little x is 15 over 64 times 2 to the power of x over x factorial, when x is 2, 3, 4, 5, and 0 otherwise. Part A. Show that Px is 2 is 15 over 32. Right, okay. As always, we might ask ourselves, what's our event space? Well, this is actually 2, 3, 4, 5. Well, this is actually 2, 3, 4, and 5. Okay. So to calculate Px2 is 15 over 32, we can just substitute our formulas with x is 2. So part A, Px is 2 will be 15 over 64 times 2 to the power of 2, which is 4 over 2 factorial, which is then again 2. Okay, so that's basically 30 over 64, or 15 over 32. Right, as they asked for, exactly. The values of 3 independent observations are made by x1, x2, and x3. Given that x1 plus x2 plus x3 is 9, determine the probability at least one of these 3 values is equal to 2. Part B, 6 mark. You can see it must be very difficult. Given, you can see the most important thing here is given. What does given usually means? When you see given in a probability question, it usually asks you to calculate the conditional probability. So if we want to rephrase part B and given formal definitions, we probably want to write it as one of x1, x2, probability of x1 is 2 intersection with, x2 is 2 intersection, union with x3 is 2. And not yet, given the condition where x1 plus x2 plus x3 is 9. And from the definition of conditional distribution, conditional probability is equivalent to P. x1 is 2 union with x2 is 2 union with x3 is 2 intersection with x1 plus x2 plus x3 is 9 over the probability of x1 plus x2 plus x3 is 9. Interesting. I think we shall start from the denominator because the denominator is usually easier to determine. You can see as previous parts where we have 2 values sum up to 80, in this part we have 3 values sum up to 9. And you may ask how many ways you can split up 9s. Okay, I think the most systematic way to count how many ways is that we're going to fix the greatest number in our sum. Let's say the greatest number is 5, then we can have 3 plus 1 or 2 plus 2, right? And we have three different orderings, right? Because 5 can be either one of x1, x2, and x3. And then actually 2 can be x1 or x2, or x2, x3, or x1, x3. Lots of different traces. You can see there are 3 factorial ways to all the 5 numbers. So that actually counts for 6 combinations, right? 5 plus 2 plus 2, 5. Because 2 actually here are distinguishable, because x1 and x3 are independent, they're different, they're distinguishable, so we have 6 of these events. Now next one, if the greatest number is 4, then we either have, so the other parts would be either 4, 4, 1, or 4, 3, 2. Okay. And again, each of them accounts for, I think, 6 different combinations. And the last one, we have 3, 3, 3. Well, that's only one possibility. There's only one possibility. That actually accounts for only 1. So now what we may need to do is summing all the probabilities together. Okay. One of the property we haven't used here is that they're independent. As I said, independence applies multiplication. So for any one of the particular combinations, let's say x1 is 2, x2 is 5, x3 is 2. This basically is probability of I actually should not ignore the 1 here, times p, x is 5, times p, x is 2, which is, let's see, 6 times 15 over 32 squared times what? 64 over 15 over 64 times 2 to the power of 5 over 5 factorial should be 120. Tough calculation. I'm probably going to go for the calculator, but for here we just calculate the next one here. 4, 4, 1. It's impossible. We can't have 1. So there's only one possibility here. 4, 3, 2. This should be p, x is 2 times p, x is 3 and times p, x is 5. Right, that's 6 times 15 over 32 times 15 over 64 times 2 to the power of 3 over 3 factorial should be 6 times 15 over 64 times 2 to the power of 4 over 4 factorial should be 24. And the last one, 333. That's basically x is 3 cubed, which is 15 over 64 times 2 to the power of 3, which is 8 over 6 cubed. Right, now let's just type all of these in the calculator and give your answer. And after typing into the calculator, you should have roughly about 0.250 to a 3 sig fig. Roughly. That's a part B. Freda chose the value of x at random until she chose x is 2 exactly 3 times. She then stopped. Determine the probability that she chooses exactly 10 values of x. Interesting. So what do we know here? So at the end, so if we want x to be exactly 10, so first of all, there must be exactly 3 of 2. And lastly, we know that the last one has to be 2, right? If we have achieved 3 of 2 something earlier than 10 times, then it will stop earlier, and you can't have chosen x 10 times, right? So let's write them down. What do we know? So among 10 times, among 10 realizations, we have 2 exactly 3 times. And then the last one must be 2. So that implies in the first 9 choices, we have exactly 2 of 2. 2 exactly 3 times. And then all the others 7 times. To simplify that for this model, we can basically written as px is 2 and px is not 2. So we know px is 2 would be 15 over 32. And then px is not 2. We have, should be 17 over 32. And now the remaining part should be easier because we can just do 15 over 32 squared times 17 over 32 to the power of 7, right? Because we need to fill up 9 times, and 2 of them are 2, and the rest of them are not 2. We can just multiply it like this. Obviously, last one is 15 over 32. Don't forget that as well. And after tapping the calculator, we should achieve 15 over 32 basically cubed times 17 over 32 to the power of 7. And the probability of this event is extremely, extremely small. You should have P should be about 1.23 times 10 to negative 3. Question this one. In the first part, I'm surprised they didn't actually ask you to use total of probability, which is the sum of all the events goes to 1. But it's even easier because for this particular question, you just need to substitute axis 2 into the formula given. No, nothing tricky. Part B, very tricky one. Here's a 6 marker. First of all, it's conditional distributions. So you need to understand what's the condition that already happened and what events are we trying to look for. So in the events that already happened, which is x1 plus x2 plus x3 is 9. And to calculate the probability of this particular event happening, we need to find all the probabilities, all the possible combinations of 3 values that sum up to 9. And we find there are 3 different factorizations almost: 5, 2, 2, 4, 3, 2, and 3, 3, 3. So we need to find and sum all the probabilities that one of these occurring, okay, which gives you 0.250 roughly. And then to find conditional distribution, we need to find the smaller events that we're more interested in. So that's the event that, given that sum of the 3 is 9, well, this probability has one of them to be 2. So you can see it's those two here, right? 5, 2, 2, and 4, 3, 2. They both contain at least one of 2. And now what we need to do is find the probability of these 2 events happening. Okay, these 2 events happening, and divide by 0.250, and you should roughly have 36 over 41, which is not too hard. You should have calculated all the separate probabilities already. But again, another part mentioned here is independence. Independence of 2 random variables means that you can multiply when trying to find intersection of 2 random variables events. You can see 6 mark. If you follow this logic correctly, you should not be able to make any mistakes. Or you might make mistakes in some calculations, but you will not miss any one of the probabilities, okay, or over-counting one of the probabilities. Another important part I want here is combinatorics, because 522 is basically means a general factorization of x1, x2, and x3, but I didn't actually assign values to x1, x2, and x3 yet. So we have 3 values, we just assign it to x1, 2, and 3. How are we going to do it? Well, we can see that x1 has 3 different traces, and x2 is got only 2 different traces now, and x3 has only 1 trace. You can multiply 3 times 2 times 1, then have 6 different traces. And roughly same argument for 432, 6 different possibilities. But now notice 333. This is slightly different, right? Because we're going to have, the only possibility here is 333. There ain't no other different possibilities. So they only gave only one probability. And for the last part, quite interesting random variable. You can see this random variable, the introduction of new random variable depends on the realization of beta facts. Okay, this random variable starts when you choose x is 2 for exactly 3 times. So you can see this random variable can go down to infinity, because in extremely small cases you can never have a 2 for 100 times in a row. That's possible. But back to our question. Determine the probability to choose exactly 10 values of x. That means we have exactly 3 of 2 in the first 10 traces, and the last one must be 2. Okay. The easier thing here is to split into 2 parts, as I said. X is 2 and x is not 2. Why? Because it's no difference x is 3 or 4 or 5 when x is not 2. Okay. So in short, we need to choose x is 2 for 3 times. So 15 over 32 to the power of 3. And then 17 over 32, which is probability not equal to 2, to the power of 7. And then multiply because they're independent again. Okay. This question. This question you can say is quite tricky. This is not so straightforward, but in a sense, the fundamental theorems we use is still covered before. And I think there are, well, to be fair, practice doesn't make everything here, because these questions are very rare. You probably haven't seen many of those questions before, but there are things we can follow. Okay, the most important part of math is you find some trend, and you generalize the trend, and you apply it to the next question. This is what mathematicians do. Okay, and talking a bit more about distributions, especially discrete random variables, they are one of the most important topics in probability theories when you progress further in university level of mathematics. They can get extremely complicated, but some fundamental things still lies on these. Okay, the total of probability, linearities, and independence implies multiplications. These are the fundamental things that we actually need to know from now, because random variables are quite abstract in a sense. But abstract means that we can apply it to a lot of different scenarios, and mastering this kind of abstractness will help you a lot in a lot of different questions. You will not only do one question, but pretty much all the questions that come up with. Okay, and that's the end for this question.